Look, I get it. You hear the word function, and you think of those weird f of x symbols that started haunting your dreams in Algebra 2. But in pre-calculus, functions aren't just equations. They are the logic of the universe. Think of a function like a high-tech vending machine. You put in a specific code, your input, and you get exactly one specific snack, your output. If you press A1 and get both Cheetos and a granola bar, that machine is broken. In math, we call that not a function. Formally, a function is a relation where every input x has exactly one output y. We write this as fx, which is just fancy notation for the value of the function at x. The set on the left is called the domain and represents all possible legal inputs x that the function can take. To determine the domain, you can ask yourself, which values of x can I plug in? Consider, for example, the function f of x equals square root of x. How do we determine the domain D? To find it, we can test some values. If we let x equals 1, the output is 1. This happens for all positive values of x. Now, if we let x equals -1, the result is undefined. This occurs for all negative values of x. Therefore, we conclude that the domain is the set of all non-negative real numbers. The tip is, if you see a square root, your domain can't be negative. If you see a fraction, your denominator can't be 0. Those are the two golden rules of domain. Now, looking at the right side, we have what we call the range. It is the set of all resulting outputs y from the domain. To identify the range, you ask yourself, what comes out of the function when I plug in a value of x? In the case of the square root example, the range is the set of all y greater than or equal to 0. This occurs because of the domain D, which is part of the function f. There are other types of expressions that are not functions. They can be represented graphically, and with the help of a method called the vertical line test, we can verify whether an expression is a function or not. One example is a circle with radius equal to 2. According to the vertical line test, this expression of the circle is not a function because the vertical line at x equals 1 intersects the graph at 2 points, A and B. However, this graph can be expressed as two functions when we split it into two separate functions, one with a positive range and the other with a negative range. Now let's look at some types of functions called elementary functions. In mathematics, they are functions built from a finite combination of basic operations: addition, subtraction, multiplication, division, and composition, applied to a standard set of simple functions. They form the backbone of pre-calculus and calculus. We can classify these functions into 4 groups. The first group consists of algebraic functions, which can be expressed using purely algebraic operations, such as addition, subtraction, and so on. These include polynomial, rational, and radical functions. The second group consists of transcendental functions. They cannot be expressed using simple algebraic operations. Within this group, we have exponential, logarithmic, and trigonometric functions. Another group is that of piecewise functions, which are defined by different rules over different intervals. Finally, the fourth group consists of special functions, such as the absolute value and the sine function. It is important to keep in mind that the number of functions is infinite, because we can combine these functions to create new ones that express different behaviors. Now, the last thing we need to talk about is the transformation of functions. I'll use the quadratic function as our main example, but everything here applies to all the elementary functions we've discussed. This is the basic structure we're going to use. These a's that you see are numbers, and by changing them, we can modify different aspects of the function without changing its fundamental quadratic shape. Let's start with the first number, the as. This coefficient stretches the function in the vertical direction. If as is greater than 1, the graph is stretched, meaning it becomes taller. If the number is between 0 and 1, the graph is compressed, or squashed. And if the number is negative, all of these effects still happen, but the parabola also flips its direction. Next, we have AH, which is responsible for horizontal movement. When the expression is x minus AH, the parabola shifts to the right, and this shift becomes more noticeable as AH increases. On the other hand, if the expression is x plus AH, the parabola moves to the left. Finally, we have AV, which controls the vertical position of the graph. As AV changes, the entire parabola moves up or down along the vertical axis. When we combine all these coefficients, we get a parabola that can be stretched, shifted horizontally, and shifted vertically. And this combined effect is what we typically see in general quadratic functions. Master these shifts and you can graph almost anything without a calculator. Functions are just the beginning. Once you understand how they move and breathe, trigonometry and calculus become a whole lot less scary. If this helped you clear the fog, hit that subscribe button. Keep practicing, and don't let the X's get you down. See ya.